So what I'd like you to do is the sections, don't pre-compile the models yet. I actually want to look at them before we, okay. Well, if it's been running, that's fine.
I ran it like a long time ago.
Oh, okay. Oh, that's fine. Oh, that's fine then.
Oh, okay.
As long as...
I ran it like as soon as we opened it, because mine otherwise I get behind.
So we're going to load a couple extra packages today, just for a couple small functions. So easy is one that I wrote a long time ago, but it's still relatively popular. I'm going to not pre-compile the models yet because I want to actually look at the data first. So
are we loading the extra code from you though?
Yes. Yeah, you can run that bit too. So there's a data file in there, mediation.csv, that this line of code here uses reader to read in. And if we just print it, it'll show the first little bit. It's a tibble, 3 columns, VIQ, NVIQ, and BDI. So this is a completely fake data set with verbal IQ, non-verbal IQ, and vector depression inventory. So we could just do a histogram. So just to view what the data looks like, we could view a histogram of each one. But I want to get a histogram of them all together. So if you do, there's a little section here to reformat. Remember, ggplot likes data in long format, so that's what the gather function does, is it sort of takes this 3 columns data and we'll turn it into just 2 columns. One column that names sort of the thing that's being measured, and the other column naming the measure in that, the measure associated with that label.
Is there a command to like make it so like, because it says 290 more rows, that you can to actually see all of it?
A quick way to see all of it is well, view.long, capital V, and that will pop up the viewer.
Okay.
And you can see all those things. That's the best way to do it, I'd say.
Like as a check to see that it all.
Yeah. Yep. So you can see instead of 3 columns, you can just imagine the columns have just been put end to end. The original 3 columns have been put end to end. And that means that we can use ggplot to look at histograms. And so we want to use the dat.long data, put score on the x-axis, add a histogram, and specifically facet so that there's 3 columns, 1 for each measure. And that's what that's going to get out. So the IQ columns are all up around 100, and the Beck depression inventories are all down sort of below 50. You guys probably already know this, but that's 63 is the maximum you can get on the BDI, and anything above 10 is like classified as having some amount of depression. So this might be sort of the measurements from a relatively depressed group of people. Mostly moderately depressed, but some extremely depressed, and some, I don't know what the lower depressed label is.
Depressed?
No, well, there's not, but then there's like a
minimally
mild. There we go. I bet you that's it. But this is what might be called sort of the marginal view of each of these variables. This is the distribution of this variable all by itself, ignoring the other variables. This is the distribution of this one, all by itself, ignoring the others, etc. So, oh, go ahead, question?
So yeah, and that was actually, I think that answered my question. So when we have it in this long view, they're no longer in any way attached. Like that's
Yeah,
the person
yeah,
who has
yeah, exactly.
a value in each one. Like they're in no
Yeah,
way
I've
Even
so
though, like,
I've ruined that.
in the stack, in theory, they're like the first person, the first of each one. Like it doesn't have them connected.
Yeah, if we could have added a like person column to this data set and then told it to keep that, like not gather that together. I only want to just show these really quickly, these histograms.
That what we did before, was did we make the other?
I think so.
Okay,
yeah.
that's why I've seen that. Oh.
Yeah. Another way of looking at this is what we're gonna is why I had you install Easy, because I made this cool graphic. Now, when I made easy, dplyr didn't exist, so tibbles didn't exist. So easy core expects a data frame, so you have to just take that original DATS data frame that's wide and turn it into a data frame using the as.dataframe. And then when you run easy core, it makes this cool visual.
Whoa.
That's cool.
Where on the diagonal is the marginal distribution of each thing. So it's the exact same as what you had here, but it's a little bit smoother looking, and each plot is just the range. It's marginal.
Yeah. Sorry. What's the marginal distribution?
The word comes from the idea that if you have a bivariate plot, so intercept and effect, or two variables, and they form a scatter plot, if you imagine all the dots falling towards one margin, it forms a nice distribution.
Margin being
Side.
side. Okay.
Yeah, they're falling to the other side. So this is for the intercept,
Okay.
and this is for the effect for this version of things.
Okay.
So what this is showing is that this is the histogram. It's hard to see under this light. This is the histogram or density plot. Is a smooth version of the histogram of the verbal IQs. This is the density plot of the nonverbal IQs, and this density plot of the depression index scores. The off axis is actually the bivariate plot. So you can see the general distribution. There's a positive correlation between verbal IQ and nonverbal IQ. That's pretty expected. The actual magnitude of the correlation is up here.
So what are the density plots? What are they showing?
They're showing, again, if you were to want to just look at what is the distribution of verbal IQ scores, it looks like that.
Okay, gotcha. And then the other ones are the correlations between verbal IQ and the nonverbal IQ. Okay, gotcha.
Yep.
Okay.
So this is the bivariate plot. So verbal IQ on the x-axis, nonverbal IQ on the y-axis, and this is the actual correlation that this sort of line
and
works
then
out
the
to.
bottom left, that's the vector depression inventory and
The
verbal,
verbal IQ.
IQ.
Yeah,
Okay.
exactly.
As well as the top.
Yeah.
Right.
So
As
this
well
is
as
a way to see like the fact that
okay.
this is like a three-dimensional data set. So this is the verbal IQ and depression score. They're negatively correlated at a point estimate for our sample of at about negative 0.8, well, negative 0.9 really. This is the verbal IQ, nonverbal IQ and the depression. They're negatively correlated at about 0.55. You had a question here?
I did, but now it may seem a little redundant. When you're talking about a marginal plot versus a histogram is the spread of scores over the range of the values of whatever score you are representing the histogram. But isn't that marginal distribution that you were showing us the range of some score, be it delta or intercept over the range, or over the length of the other score?
No.
And that's
Their
because you're
histogram
not, yeah.
of the
No,
single variable is what I
just
mean by
realized
marginal.
that
Yeah.
The axis that we're collapsing over is the axis that's
Yeah.
represented by the range of the scores, and therefore
Yeah.
it was a bad question.
All right, so this is just another sort of descriptive view of the data, in that, in the same way that we can ask sort of how is each variable sort of distributed itself. This is showing how sort of each pair of variables sort of generally distribute with one another. And when we do this, when we do any sort of multivariate data analysis, we're going to be including a correlation matrix. So before we just had two things. So imagine that this was the VIQ and an NVIQ, and we just have a single correlation to estimate between those two things. When you have three things, you're going to have three correlations to estimate between them. We actually did have a scenario like this at the very end of the class where I introduced this multivariate repeated measures. But we went through it pretty quickly. So I thought I'd do another version of it and specifically talk about this idea of mediation analysis. So mediation analysis, usually when it's described, takes the form of boxes. So let's say so this is verbal IQ, this is nonverbal IQ, and this is depression. Now, we already know that this is going to be a strong correlation between these two things. We know, maybe what we want to know is how does verbal relate to depression, and how does nonverbal relate to depression. And I've actually already shown you guys how to do this, in that it's just here's sort of point estimates of how looking at this one, this is sort of the magnitude of the relationship between verbal and depression, and this is the magnitude of the relationship between nonverbal and depression. So let me actually just add those in. So this is negative 0.88, and this is negative 0.5, what was it, 55?
Yeah.
55. Did I get 557788?
Yeah.
Neat.
Just out of curiosity, how would you measure or model, I guess, the effect of what's D? D is depression?
Yeah.
Yes. How would you model the effect of depression on the relationship between
Those two things. We are, I think, save that question for, ask me that after class, because I think that's possibly just falls out of this. So critically, any of these arrows actually should be double-headed, because correlation isn't causation. We can only ever talk about the strength of a relationship. But each of these arrows kind of reflects like the overall relationship, but doesn't. A separate question that people often like to ask is, what is the relationship between verbal and depression once this separate set of relationships has already been accounted for? So 0.77 and negative 0.5. So we know that there might be a direct route for verbal to affect depression. I'll do it ... But there's also an indirect route whereby verbal is related to nonverbal, and nonverbal itself might have its own sort of independent prediction of depression. So what we want to know is, what are sort of the independent utilities of verbal and nonverbal with regards to predicting depression? When I say predicting depression, it's the same as saying the relationship between these things and depression. So does anybody happen to already know what sort of these dotted lines would be called if it's saying this relationship independent of the other relationships?
Mediation?
Well, it's the general idea of asking about these extra having these overall relationships, but then also asking about these independent ones is mediation. Yeah.
Partial correlation?
So yeah, that's what that is these dots are the partial correlations.
Okay.
So fundamentally, a mediation analysis is asking, okay, given these correlations, what is the partial correlations between these things? So let's actually, though, just start with the question of what are these correlations? So we've got the point estimates that we can just compute from our data of 0.88 and 0.55 and 0.77. But what we actually want to know sort of what are credible beliefs about these correlations. So that's where our model actually comes in. If I go to Files and I look at, it should be just mediation.stan. And while we're looking at this, so open it up by clicking on it, but then go back to your mediation.r and tell it to compile. So the medmod equals rstan, etc.
And the second one too?
Sure.
Wait,
Yeah.
so we're doing the pre-compile thing?
Yeah. So that, yeah. So I've opened it so I can talk about it while it compiles.
Oh, so we're not changing any of it. You just
Oh, mine's
Yeah.
an unexpected symbol in pre-compile. Oh no,
Oh.
I think that was just
Gotcha.
a highlighting
Yeah.
thing. Yeah.
So this actually is going to be very familiar looking. It's in fact, we actually wrote this model at the very end of the class where we started talking about multivariate data. This is the one where it's being generalized to handle data sets with any number of columns, where each column is a sort of measurement of a person. So we've got 3, verbal IQ, nonverbal IQ, and Beck depression. If we had measured other things like an anxiety measure or anything else, this same file will work. The data coming in is expecting something called N, which is just the number of sort of cases you have, number of subjects. K is the number of things you're measuring in each subject. So number of columns. Here it's going to be 3 for us. And Y is just going to be the data set. It's the with N rows and K columns. So a little less, like, we don't have to do as much as in previous scenarios where we had to create a model matrix or things like that. The parameters section, well, remember our model is going to be that every parameter is going to have, every measure is going to be modeled as having a normal distribution with some mean and some variability. And then on top of that, we're going to have, for every pair of parameters, we're going to have a correlation between them. So we've got 3 columns in our data set, verbal IQ, nonverbal IQ, and Beck depression. So we'll have 3 means, a mean for verbal IQ, a mean for nonverbal IQ, a mean for depression, and we'll have 3 variabilities, one for verbal, one for nonverbal, one for Beck depression. And again, those variabilities reflect how variable one person is to another on each of those scales. And then finally, we'll have a correlation matrix of size k. So when there's 3 columns, there's actually 3 correlations that could be. So we'll have that correlation matrix. So we set it up so that there's a vector of size k. So there's a vector with 3 items in it called mu. There's another vector bounded at 0 with 3 items in it called sigma. And then a correlation matrix of size k called rho. So that's going to create 3 correlations. We had this little bit before where when we start out our expression of our model, we had to say, oh, wait, there's this other thing called Z, and that's the covariance matrix. In the same way that a correlation matrix is going to be of size k, a covariance matrix is going to be of size k by k. You don't really need to worry about that at all. It just needs to be computed. The covariance matrix is computed by combining the correlation matrix with the variability of each measure. So that's what this little line does. And then the rest of our generative model is simply saying that we loop over subjects. That's what this little bit is doing. It's saying for each subject, every subject's data is sampled as a multivariate normal distribution, where each sort of dimension of that multivariate, you could think of the case where there's 2 measures. So here we have the case of something called I and something called delta as a 2-dimensional shape. Each measure here had a mean of whatever these 2 things are. So we had this would be a 2-dimensional vector with mu delta and a mu I. And the combination of these sigmas and rho determines that covariance matrix Z. If you have the 3-parameter case, it's saying that the data is coming from a 3-dimensional plot, so we can't actually show it on paper. We mentioned sort of a dot cloud. Again, where each dimension has a mean according to the means in this vector, and then a covariance matrix that it is just all figured out from the correlations and the variabilities. Now for the 3 parameters we have here, we want to specify priors on those parameters. So we've got mu, sigma, and rho. This code assumes that we're going to scale the data. So once we scale the data, these priors are going to be pretty standard. So normal 0, 1 for mu. So all the dimensions, we will actually prescale them so that they have a mean of 0. So this will be fairly broad prior for the centers. We're also going to scale each dimension so that it has a standard deviation of 1. So it makes sense to have a log normal prior. This means that this is a prior where sigma, we have peak credibility of sigma values of 1, and it falls off on either side. And then for rho, I just told you that sort of a good uninformed prior for rho is this LKJ core thing with a 1 inside. And all that's saying, that takes care of the fact that when you have a correlation matrix, there are some correlation matrices that are impossible. So you couldn't have a correlation matrix where 2 of the entries were 0.99 and the other entry was 0. Like that just can't happen. The different correlations have to add up to something called positive definiteness. Something that I don't fully understand myself. It just means that like there are some scenarios where you can't have 2 things ridiculously strongly related, and then one of those things is also ridiculously strongly related to a third thing. But so if you have A, B, and C, A and B really strongly related, A and C really strongly related, B and C by definition now have to be really strongly related. You can't have like 0 correlation or a change in the sign of the correlation. So there's when you start having correlations amongst more than 2 things, you have to have some restriction on what correlations are possible. And that's what this little bit ensures, is that you're expressing a prior that's uniform across the space of possible correlations, but it only deals with possible correlations. You don't really ever have to modify this unless you actually want to start. Frankly, I don't think I'll ever be advanced enough to start or get into complicated enough data that I'll want to change this. So you could just think of this as just ensuring that the correlation works out. So what this is going to give us is, in theory, the same sort of thing that you get in the graphic over here. It's going to give us a correlation amongst all these variables. It's also going to tell us where each variable's sort of center likely is and how variable each measure is. But it's going to give us a credible interval on each of those properties. So I should be able to go back and, having compiled medmod, scroll down maybe in my table of contents here, sample the model. It's this section. So we package up the data for Stan. Again, Stan wanted something called N, K, and Y. N being the number of observations, K being the number of columns, and Y being the N by K matrix. So N is just the number of rows in DAT, the number of people we have. Each row is a person. Each column is a measure. K is number of columns in DAT. And I said we were going to use these default priors in our Stan code, which presumes that out here we're going to do something to scale each column so that it has a mean of 0 and a standard deviation of 1. And that's actually what will happen if you just provide DAT as the value to the first argument to scale. That scale DAT spits out a scaled version of the data that you put in. So
I do have a question about the line before. So number of columns for k equaling k, I'm assuming you want k to represent the number of different variables
Yeah.
you have. But if you have an ID variable and you don't want to count that in,
You'll want
how do you
to, if you
modify
know
it?
that there's an ID variable, you just say minus
Minus
1. There.
Cool.
That's the quickest way of doing it.
Is it -1 because
Because there
the
were
position it's in, or does that matter in this case? It's just -1.
Uh,
It's one you want out.
Because there's just one that you want out. Yeah.
So if there was like more than one that you wanted out?
Yeah, if that's the case, I'd maybe modify the data frame. Remember, we have that in dplyr, you've got the select thing, so I'd create something called dat2, or actually,
That just has the variables you want.
yeah, I guess the way it would work is dat pipe to select, and you'd enter the variables you want. Select also allows you to say the variables you don't want, so I'd say, if ID were a column I don't want, I'd say negative ID. If, say, age were in there and I didn't want to add age, you'd do that, and then you'd put it into something.
I guess I'm
For
thinking
example.
about like, I'm working on analyzing my comp data right now, and there's
Mhm.
literally like 200 variables in there. And if I only wanted to do a mediation with the 4 variables,
Mm-hmm.
how do you do that if you don't just have a data set with just those 4 variables?
Well, you'd give the names. So let's okay. You'd say to use the dplyr and select syntax. You'd take dat, you'd pipe it
What does
to.
the pipe do again?
It just says I'm going to work with this data set. So anytime I refer to the names of columns thereafter, it's going to look in this data set. So if you happen to know the names of the columns you want, say it were height, weight, I don't know, sick, and say those were the names of the columns, that would, and then you finally store that into a new object. How do? Oh, you would just put an arrow at the end, a right pointing arrow.
Okay.
That would create a new object called dat2 that just had those columns.
And then you just work with
And then this would work just fine.
it. Okay.
But we're in a scenario where we just have the columns in our data set that we want, so we can package it, put it into that list in an object called data for Stan, and now we can sample. Takes a couple minutes for all 4 chains of 2,000 iterations each to run in serial. If you were, oh,
I don't know where, like, I feel like this is going way back, but then the question about not including certain columns just got me thinking, I don't realize how do we, at what point did we tell it which 3 columns to look at?
aha, it's going to take everything in dat. So dat right now is just 3 columns.
Oh, okay. This one we didn't have a.
ID column,
we didn't
no.
have an ID.
No.
Never mind. Did we ever notice that an ID column?
I think maybe back in like the first day.
Okay.
Sorry, not the first day. The first time we did multivariate data, I actually went through a example like this, and it probably had an ID column.
Okay.
Yeah.
While I was running, I was wondering in terms of what you were showing us, where there's kind of the 3 variables and we're
Mhm.
trying to do the partial correlation with the 3 of them. Is it possible? I was thinking of my data set. We have cognitive impairment in MS, so like MS on the left, cognitive impairment on the right, and then we have depression up here, but we also have anxiety.
Mhm.
Can we put like
Yeah.
can we look at the
Yep.
effect of 2 variables?
Yep, like if you are imagining that, let's
Because like we know
do it. You've got
depression, anxiety, or with a correlated cognitive impairment, we know MS point is correlated to cognitive impairment, but don't know like the connections between them all.
And what's the cognitive impairment?
Yeah.
Out here, and is there, what was
and
over?
then it's like where you are in your MS progression.
Okay. So this would be a model where you have a correlation, sort of a direct route there. I'm just going to draw lines because my arrows suck. You have an indirect through anxiety, indirect through depression, and then you might have some sort of association through that. That you can sort of, the way where you draw these things actually doesn't matter. This is just another correlation matrix. And so you can talk about what is this correlation, what is this correlation, what is this correlation, what is that, what is that, and then what are all the partials.
So just adding another variable.
Adding another variable, you just add another column to your thing, and it'll all, at least as you've described it. So this will all work for the scenario where each one of these is just a continuous measure. I'm going to have next day a scenario where you say have data where there's like an effect per person. So you have like, we'll get into that another day. But
What if you wanted to do semi-partial correlation? Would it just be a matter of restricting the model such that it doesn't calculate one of the correlation measures?
You can. We'll have to talk about that a different time. That is like structuring the model such that you have, you're asserting that one relationship is independent. And we can do that. It's just when the model can estimate all the correlations,
You might as well.
that's like the one you're describing is like a subset of the more general model that we're using, and you can ask your question. Like so your model makes an assumption of independence for a certain pair or set of pairing of measurements that you don't need to make that assumption if you do the full model, and then just afterwards you can say, oh yeah, that's assumption would have been valid if we had it, but we don't need to make it in the first place. So you would be able to look at those correlations, see that they're mostly sort of 0 is still a really strong credible value for those.
Yeah, there's no harm, I guess, in this case of doing an exploratory thing at first
Yeah.
to determine if a correlation exists.
I even wouldn't follow it up with anything.
If it's just a blank and you come up
Yeah.
with something including or a credible interval that includes, in this case, 0 for no correlation. Just leave it as
I
such.
wouldn't. Yeah. So, okay, we're getting back to our actual model where we have these 3 variables, and we want to talk about their correlation and eventually partial correlations to talk about the mediation type model scenario. So we can look at this and we can see that after each iteration each chain got through, we got this little warning. I think we saw that last time, but I showed you that if the number in the count column here, it's hard to see that there is a column, particularly if you have a compressed view of things. But there's a column here under count, and if that number is substantially less than the number of iterations that you asked for, you're okay. And that's exactly what's happened here. This actually is a consequence of sometimes it tried a correlation matrix that's impossible, and it realized, hey, this is impossible, in which case it said, oh, okay, never mind. So we've run through, let's take a look at the posterior estimates for each of our things, which we can do by saying print of post. I actually have these extra lines in here to make it look a little bit prettier, not to have as many digits in the output, and ask for only the 95% credible interval points, 0.025 and 0.975. So we're going to have distorted image over on this side, but mu1, 2, 3, those are the center points for the means for each column. Remember, we actually scaled the data ahead of time, so those center points should be about 0 in the first place. So those can pretty much be ignored. If we want to actually get the posterior on the mean for each of these things, we would add back in the mean, the observed mean to each of those, and that would create a new posterior. And multiply, well, we'd multiply by the standard deviation and add back in the mean. We're not, for the given question of the relationship amongst these things, we don't actually care about the centering, so we won't bother rescaling. Ditto, these sigmas are all going to be about 1, and that's as intended because the way we scaled the data. So it's the row bit that we're most interested in. And annoyingly, because rho represents a correlation matrix, it's not like able to show the correlation matrix in the nice visual format that you might expect. It shows, okay, here's what you should believe about, and in brackets it says what cell you're talking about. So 1, 1 is the upper left corner of the correlation matrix. Let me actually draw out the correlation matrix too.
Could you not like call them these individual values out, or are they not even like I technically guess it's not really an object in R. The results. Of the
no.
model.
Yeah.
Could you assign it to a variable and then call out aspects
Yeah.
of it?
Oh yeah. Yeah. You can name things better. So we had VIQ, NVIQ, and depression. VN depression. So along the this axis, it should all be 1. So we can, whenever we see 1, 1, 1, 2, 2, or 3, 3, we can ignore that. We should be 1 in all those columns. So the critical ones are the off diagonals. So this one is 1, 2. So the correlation between V and N is, sort of has a mean in the posterior of about 0.76, credible interval in the posterior 0.67, 0.83. So strongly correlated. It's relative to our point estimate. It was 0.77. So centered on our point estimate, but this expresses our credible interval for it.
Sorry if I missed this, but how come it doesn't it usually show the 50% too?
Pardon me? I took it
Just
out.
put it in.
Yeah, so see over here when I said print
in the
post,
right.
probs
Got it.
equals, and I just gave it the 2 points of the credible interval. So that's the correlation between verbal and nonverbal. The correlation between verbal and depression would be 1 and 3. So here it's peaked at negative 0.87, which is very close to the point estimate that we had from the data of 0.88. But critically, our credible interval ranges from negative 0.91 to negative 0.82. So we're pretty confident that it's a strong negative correlation there. And finally, the correlation between the nonverbal IQ and depression, that would be column 3 still, but row 2 now. So it's 2, 3. First number is the row, second number is the column. So looking at 2, 3, similar to what we had as a point estimate for the mean, about 0.5-ish. And the credible interval here is now negative 0.36 to negative 0.65. So pretty confident that it's negative. Pretty confident that it's sort of in the moderate range of negative. And that's the correlation between verbal IQ and depression is stronger than the correlation between nonverbal IQ and depression. So those might be, unto itself, those observations would be sort of useful. But we also had this question of like the independent contribution of each thing what is the independent sort of relationship between each pair once the other relationships have been taken into account. That we didn't get our stand code to create that, but it turns out that if you've got a correlation matrix, there's just a simple mathematical procedure to determine what the corresponding partial correlation matrix is. So in the same way that you get a matrix saying what's all the correlations are, you're going to get a matrix that specifies what all the partial correlations are. So I made a little function that wraps up the math that you need to do, and that's what you did way up above when you said source this file. It's because in that file I wrote some R code that does the computation of the partial correlations from the correlations, and specifically grabs the correlations from the this object post so that we can then grab out the different cells of that design. So this creates a thing called PCore, which is just samples from the posterior. We actually have to compute these quantiles ourselves. You don't get a nice printout, but we can do that. Remember, so this syntax, PCore, and then square brackets, empty, and then comma, 1, comma 2. So the empty means this PCore thing is a 3-dimensional object. The first dimension has all the samples across all the chains from the posterior for that cell in the design. The next 2 dimensions are the dimensions of the correlation matrix or partial correlation matrix. So
What's the first dimension?
it's the samples from all the cells in the design. So if you imagine that we had this correlation matrix and I was just stacking up in space the samples for that cell. So if you imagine it's sort of going,
So it's like the number of observations?
yeah,
So
there's
like blank, you're
so there's
counting all the
4,
observations.
yeah, there's 4,000 observations in this, 4,000 observations in this.
Can we leave it blank? Just,
To say that I want to
Default
grab
to
all the observations in that dimension.
or just let it default to whatever they
Yeah.
actually were. Okay.
So PCore, comma 1, comma 2 is grabbing the verbal IQ and nonverbal IQ. So we can look at the partial correlation between those two things. And it's 0.73. It's actually not changed too much from the first one. If you look at the point estimate and credible interval, they're fairly strongly overlapping. The next one, the quantiles for 1 and 3 is 1 being VIQ and 3 being depression. So we can look at that partial correlation. That hasn't really changed that much either. But the final one, partial correlation between nonverbal IQ and, this should say BDI, if you have in your, will show a strong difference from what we had. So again, up here we have the correlation 2, comma 3. So it's this one. It had a negative sort of mean credible interval that ranged from negative 0.36 to negative 0.65. Now the partial correlation is actually positive 0.28 to 0.58. So what that's saying, and what you would typically see in papers, is you'd probably also see, little asterisk saying that the credible interval on that excludes 0, credible interval on that excludes 0, credible interval on that excludes 0. You'd have for the partial correlations, I think it said like 8.7. What was the 8.6 would be the median if you wanted that there, so 8.6. So little asterisks. 7.3 for this one. And then you say 4.5, yeah. So 0.45 for this one. So that's typical sort of outcome most mediation people will expect to see. You see the sort of the direct path, or sorry, the overall correlations, but then you also get the partial correlations expressed.
And all we're looking for to get the asterisk is that it doesn't cross 0.
No. If you're, again, using this
Yeah.
interpretation of the Bayesian result to say, if 0 is not in that credible interval, we can conclude that 0 is not very credible. Therefore, we'll call it significant. Say there's a difference. Say there's a relationship. So I'll note that what is actually happening here, in contrast to other sort of tools that deal with mediation analysis, is that I guess behind the scenes, any of the frequentist mediation analyses that you've been doing or that you've been exposed to will actually try to fit multiple models. It will, for example, try to fit a model predicting depression from nonverbal IQ. And that will yield one measure of relationship. And then it will fit a second model where it has both of these predicting depression, or both of these relating to depression, and that will yield another value for the relationship between N and D. And they compare those two strengths of relationships. In theory, if there's this other sort of amount of predictive, this other pathway for the relationships between N and D to occur, that second model that has that relationship in it compared to that first model should have a smaller value for the correlation. And people are able to establish what this what the credible interval is on this partial correlation by talking about the degree to which that variability has, like, you've increased your predictive power by having just this model versus both models or both variables. We've been able to do it in just a single model that is able to generate these credible intervals for each of the partial correlations from the correlation matrix that the model has. So it's a little bit more straightforward than...
Is it able
Now-
to take more variability into account because it does it all in one model? Like,
No, I mean, functionally, it's, for you as the user, it's achieving the same end. It just, they do different things behind the scenes. There's multiple models being fit in the frequentist world, and then they try to derive sort of a test of significance from a difference between the models in how well they fit the data, like what sort of variance reduction they get from fitting the data, whereas we're just fitting a single model and getting expressions of what we should believe about each of the parameters.
I have a question.
Yeah.
Sorry, you first. So I could be like totally missing the mark here, but in my head, when I think of mediation, it's like when you add the V, which is the mediator, then the relationship between N and D becomes non-significant.
That's what and that's the conventional way of talking about it, is that the only way people were able to formulate how to get out a test of this thing down here. I mean, you could always compute it, but to actually express a test of this thing, the frequentist tools didn't have the ability to express like a confidence interval on this or a p-value on this. So what they would do is they'd fit two models, one with this relationship, with just this relationship, not having V in there, and so that would have a value down here that actually probably would be a lot bigger than 0.55. And then they'd have a secondary one where they were able to compute not only the partial correlation, but what this new correlation was. And the comparison of like, what does adding V, as you're saying, what does adding V to the model do to this relationship is what they use to assert a test on this relationship, this independent relationship. We don't need to do multiple models. We just do it from here. Because we're able to extract the credible interval on this thing, whereas it's not really defined for like the frequentist version of this model.
So I don't know if maybe I'm wrong, but I never learned it as it being not significant without it, just that it changed the
Change
strength.
significant. That's a moderation, not a mediation. Moderation is changing the strength of the
Wait,
effect.
I think what she's saying though is that like that going from the 0.55 to like there might still be a correlation, but it just because that's where you get into like partial mediation
Yeah.
versus like full mediation.
Right. Yeah. Does that make sense? Yeah.
contrasting the frequentist, like significant, non-significant, or degree. So what are we saying here compared to the frequentist?
Well, we're, again, the actual end product of being able to say what is there sort of a significant relationship between nonverbal and depression, independent of the relationship that these two things have and these two things have. We are able to say whether there is that relationship or not, and what magnitude.
So it doesn't really include like the mediator at all?
Well, it's saying that, if you wanted to talk about the degree to which V is...
Explaining.
Yes.
Because when you could still see that though in the difference between the first correlation and the partial correlation. Like if the partial correlation changes a lot, or say if the credible interval for the partial correlation includes 0. But now we're getting back in, like, I don't know if it's just me imposing how I learned it before onto it, but like if for the partial correlation, if the credible interval includes 0, then like that the correlation between those two things is just due to the correlation between other things?
Yeah. Here's another way of thinking about it. So the idea is, if we were to go in and observe, ignore these internal partial correlations. So the frequentist is able to go in and observe, if I have these three things, there's this relationship between nonverbal and depression. How much of this relationship is mediated by this other sort of pathway of the relationship? Is that your sort of understanding of that? And in order to answer that question, they have to do a whole separate model where you just have these two things, and then you evaluate to what degree did the sort of measure of this relationship here differ from the measure of the relationship here with all three. And that's because with any correlation matrix, you can just get out if you have a point estimate for the three correlations, you can derive what the partial correlations are, but that doesn't tell you about like the credible intervals or confidence intervals on those in the frequentist terms. So they have to, in order to derive confidence intervals on these partial correlations, what is the independent contribution, what is the independent amount of relationship between these two things, they have to do two models and then do a comparison of those two models. So we don't, in the Bayesian world, every parameter in your model, including these derived parameters, the partial correlations, will get its own credible interval automatically. So you don't need to do two models. You just do the one model that includes the full set of relationships, and you ask, what is this independent relationship like? If this independent relationship were to be 0, that would suggest that nonverbal IQ doesn't have a role, and verbal IQ completely mediates the role that nonverbal IQ has.
So you wouldn't run, I guess, because like for mediation, the first step is like you run like regressions with just your variables of interest, and then you're like, okay, now these all make sense, and this one seems like it might be mediating this effect, so then you run the mediation model.
This, you put them all in, let Bayes sort them out.
But you can still make the same conclusions, right? Like
Yep.
what you just said. So like we're putting these all in and we're getting all of the partial correlations all at once. But so like, because like the correlations that you have on the outside there, those would be the same. Like if we just had like 2 of those variables in our model, like that would be that same correlation, right? It's just the straight up correlation between
Yes.
those 2 variables.
Yep.
So like the partial correlation, like if this one at the bottom was the credible interval includes 0, then you can still make that same kind of interpretation that like it's now gone to 0, and so this third variable fully mediates that relationship. Yeah.
So now it's just like partially mediating it?
Yeah, right now it's gone from negative 0.55 to to, on the other side, well, about negative 0.5 to about positive 0.5. So you've had like a big switch. Now, it hasn't gone all the way to, well, I don't know what you talk about in terms of a scale of mediation, but certainly it's a non-zero mediation. If the inside were also negative 0.55, or sorry, if the inside were 0, i.e. It didn't express a mediation, that would say that this, there was no relationship between these two. It would mean that this accounts for the entirety of the outside relationship.
So it's still kind of the same thing.
Yeah.
Okay.
Yep.
It just does it all at once.
Yeah.
Instead of having to run this one, this
Yeah.
one, and this
Yeah.
one.
Yeah, exactly.
It also just seems like it never assumes that everything is independent. Like it seems like frequentist has to run a model where it's assuming that the variables
Yeah.
are independent, which doesn't
Yeah.
make sense in this case.
Yeah.
So this model is
Well, the frequentist will run like subsets of these models and establish, okay, what is the relationship when I pretend I don't have other information? And then it tries to establish, okay, and now how do my estimates of the relationships differ across these models that are being given different information? And that's how they establish the significance or not of this. We just don't need it. We just do it all and have we have our credible intervals on everything that we're interested in. It's going to show you a more sort of direct way where again, to the end user, there's no difference because the frequentist tools automate that and do it all behind the scenes for you. Something that is kind of user-facing is the ability to do. I talked about this a little bit in one of the earliest classes. I thought I'd give you guys an actual example of it. This next section, if you go on the table of contents, add some outliers. I actually literally add a bunch of data to our existing data and create something called DAT2 as the result. So if we look at the new plot, if you compare the two, there's a few extra data points that I added. And the consequence of adding those data points is that it has dramatically reduced the estimates of correlation here, the point estimates of correlation for the data, because I actually wanted them to be outliers both in terms of, so these actually aren't outliers like if you look at the univariate distribution or the marginal distributions, these points still fall within the data. They're what would be considered bivariate outliers. So they kind of are opposing to the overall cloud of data. They're outliers in the sense of the two-dimensional cloud of data, but not with regards to any one dimension. So they'd be kind of hard to actually detect, and these are sort of hard to deal with typically. Let's go, so what do we do in a scenario like that? Well, I told you about this earlier, that you can use robust models, and I'll go through this quickly because we have 5 minutes left. I'll get you to open up mediation_robust, and once that's opened up, you can go up to the top.
The stand file?
Yeah, so mediation_robust, just click it, and that should open it up in your little viewer here. And once that's done, you can go back to mediation.r and tell it to compile. If you haven't already, it's okay if you've already compiled. That's fine. Actually, so run the line there to start it compiling. While it's compiling, we can go and actually look at the data. Everything in this is the exact same except for the very last sort of line down here, line 24. So I still have mediation stand open, so I'll go to line, I'll just put it there. And what I've done, so here we're saying each person's observation is drawn from a multivariate normal distribution. Here, it's saying each person's observation is drawn from a multivariate student T distribution. Normal distribution has that nice bell-shaped. Student T will have the same bell shape, except it's got the thicker tails. It actually has a parameter to say how thick you want the tails to be, and that's that first parameter. 1 is like the most extreme version of the student T.
So it's like the most conservative.
It's the one that, yeah, that's sort of, yeah. So what this will do is it will make it so that these outliers aren't as influential.
Okay.
When there's outliers in your data, this model will say, oh, okay, that's those. It will be more sensitive to the data near the middle of your data. So that is actually compiled for me. So I'm going to use my table of contents here and go to sample the data, sample the model with data containing outliers. So we created this new thing called data too, so we'll need to repackage the data. So I'm creating,
How are you getting to that like little?
at the very bottom. Do you see that
No,
in yours?
there's nothing to click on.
I wonder, I had some people install RStudio Preview, and some people only install, possibly only install regular
I'll just
RStudio.
scroll down.
Yep, okay. So sample the model with data containing outliers. So we've got new data, so we need to actually repackage it. So we'll create data for stand 2, but it's packaged the exact same, this time only referring to data stat 2. And once that's packaged, we can sample, creating something called post2. Pardon me?
I don't know.
Compiling or
Yeah, like
doing this?
It's been stuck at 40% forever.
Ah.
Do I want
Ah.
sample the model with data containing outliers or sample
Yeah.
the robust model with data containing
Aha. So I actually, forgot what I was doing here. So first we're going to sample the non-robust model. That's, yeah. So if you were to assume, if you were to still use the original model we used that said, okay, use normal, but you have data where we've added these outliers, then you're going to have some issues. Let me... our observed correlations are going to be much smaller than they were earlier. And if we go, the next section is getting the partial correlations. The partial correlations won't be quite as sort of strong. They're all still significant in the sense that they all exclude 0, but this was quite a bit stronger before. So the presence of those outliers has diminished the statistical power. I happen to have enough data in this already that it hasn't changed any of the substantive conclusions. But if I had, say, so there's 100 people in this study and I added like 3 or 4 outliers. If I had far fewer people, those outliers would become more influential. So if we, what I wanted to demonstrate here is now if we use that same outlier included data, but now use the robust mediation model. Should go to spoil. We'll get the same general credible intervals that we had for when those data points were not in the data at all. And I'm not aware of any of the Frequentist tools being able to just, with one like word change, be able to account for potential for outliers.
So would you recommend always using the robust one?
I haven't seen a scenario. So it costs. All it does is cost time with more complicated models. We haven't got to any of those scenarios yet. Hierarchical models with many observations are going to start getting, it's going to start costing time, but for what we've done, generally there's little cost.
It was like Sean McKinnon, when we run like frequentist stuff, he's always like, yeah, just always assume unequal variances. Like there's an option to do that, just always do it. So is this kind of like the same thing?
Yep.
Okay.
This is just showing we're getting out those credible intervals that we had before now that So the model has been less influenced by those outliers. And there's actually a way, I haven't done it, but there's actually a way to, like, because in theory, if you guys, the student t, I told you, it has this parameter here that tells you how thick those tails are. If you put it up to like 100, it's pretty much equivalent to a normal. Like so. The bigger this number is, the closer the student t is to a normal. So you can actually do inference and ask, like, how outlierish is my data? And you can turn that parameter into, sorry, that value not as a fixed value, but as a parameter. Tailoredness. You can add that as a parameter that you're actually estimating from your data. In which case, you kind of get the best of both worlds in that you actually are estimating from your data to what degree you need to be robust, which is kind of cool. Anyway, yep, that's it for today.